Welcome to Business Statistics. Today's lecture deals with basic probability concepts. During the first half of the semester, we will be talking about probability theory. Probability theory is the mathematics of uncertainty. Anytime I want to describe my uncertainty about something or communicate my uncertainty about a business situation, or analyze my uncertainty, or, and most importantly, incorporate that uncertainty into the decision-making process, I need probability to do these things. Let's look at the two words that we should add to your vocabulary. The first is stochastic, meaning that a situation has uncertainty. A stochastic situation has uncertainty. Its anonym or opposite is the word deterministic. Deterministic means all of the factors involved in this situation are known. If we have a restaurant who's making their special for the evening and it takes several hours to make, how many meals should they make ahead of time? They don't know what demand's going to be in most cases. So we have an uncertain situation. If we have FedEx who at 6 o'clock, we know all of the packages that have to be delivered and we want to minimize the total mileage in delivering all the packages worldwide, that is a deterministic problem. It's a huge problem, but it is deterministic. Adding a couple more definitions, a random process is any operation where the outcomes are controlled by chance. In other words, it's any situation that I have uncertainty concerning. In any random process, if we exhaustively list every possible thing that can happen from this random process, we get the sample space. It's the exhaustive listing of everything that can happen from a random process. Sometimes the data in our sample space is quantitative and sometimes it's qualitative. If we're uncertain about say the next individual who makes a purchase on our website, that person's age is a quantitative data. The person's height and weight are quantitative data. The person's marital status and gender are qualitative data. If it's a female, that female's dress size is a number, but that is not quantitative data because you cannot do arithmetic with it. A size 4 is not twice the size of a 2 and half the size of an 8, and a size 0 doesn't represent the absence of a dress. It represents a small size. Some of our elements in our sample space are discrete, meaning there's gaps in there. If we have discrete data, we have commas in our sample space. And if it's continuous, we just have ranges. Technically, someone's weight is a continuous random variable, and we could weigh them on the most accurate scale we have to get it to pounds plus many, many decimal places. But our convention is to round it off to the nearest pound, so we treat it as a discrete random, as discrete data instead of being what it really is, continuous data. Obviously, continuous means finite. Discrete may or may not be finite or infinite. An event is any subset of the sample space. And what we'll be doing for the first half of the semester is taking a look at the probability of various events. And again, an event is any subset of the sample space. Probabilities come to us in three varieties: the theoretical or classical, empirical, and subjective. All of the early work in probability theory was done in theoretical probabilities. Most of the work, early work in probability theory was done to improve the gaming skills of the lord or lady, where the mathematician was being subsidized. Girolamo Cardano is an Italian mathematician from the 1500s. We wouldn't call him a statistician because the word statistics didn't really exist until 1850. So we call him a mathematician. He was the first one to do any groundwork in probability theory, and he came up with the idea of odds. If I want to know the probability of drawing a heart from a 52 card deck of cards, there are 13 cards out of the 52. Or you could also look as if there's 4 suits with equal number of cards. Either way, you get 1 out of 4. Probability of not drawing a heart is obviously 3 out of 4. What are the proper odds if people are going to wager on whether or not they can pull a card out of a deck? What would the proper odds be? Well, if you bet $10 and claimed that you could, when you cut the deck, there would be a heart, proper payoff for your $30, your $10 is if the a heart is, if you cut the deck and a heart is seen, then you make $30, $10 times 3. And if you cut the deck and find any other a suit there, then you lose the $10. That would be the proper payoff. Empirical observations. These are things where we've collected data, observations from industry. If I write, our convention is P means the probability of. So P of, and whatever's inside the parenthesis is an event. If I want to know the probability of a defective part, I'll look at the total number of defectives that the manufacturer has produced over the total number of parts they produced, or I'll take a look at the total number of defectives they've sent me over the total number of parts I bought from them. So most of the time in business, we have some empirical data. As we saw in our introductory lecture, the amount of data that's being produced is growing exponentially. A subjective probability is opinion-based. If we're on the bleeding edge of technology and we have no historic analogies, no data out there concerning what it is we're trying to forecast, then we must go with some kind of opinion. Hopefully it's an expert opinion. The example would be the probability that the Rams win the Super Bowl. I think they got a decent chance. You know, I might put the odds around 8 or 10, 12%, maybe something in that range. Other people have varying views, and that's what makes life interesting, especially to the sports book. When people have different views, they have the different subjective probabilities, they have a reason to make a wager. Probability theory is a theory because it is based upon a set of axioms. The first one means that probabilities are scaled between 0 and 1. The probability of any event E happening is less than or equal to 1 and greater than or equal to 0, where 0 means no chance and 1 means certainty. When I add up all of the probabilities in the sample space of all of the events in the sample space, the sum of those probabilities must equal 1. We're going to take a look at 4 operations here where we, when we're talking about events, I sometimes want to take a look at the probability of 2 things happening simultaneously. So if I have, let's say, 2 bids out on 2 different contracts, I want to know what's the probability that we land both contracts, and where I might have to do some plant expansion in order to meet those 2 contracts. So I want to know what's the likelihood of that happening. The intersection sign we'll be using for the AND operator. If you don't like using this intersection sign, don't bother, just use the word AND. That will be fine with me. If I want to talk about 2 things happening simultaneously and I write it like this, what's the probability that A and B occurred simultaneously at the same time? It doesn't matter the order that you list the events with an intersection because it's commutative. Okay, the order doesn't matter. They both happened, and the order of listing has no bearing. Other words that mean an intersection are both, all, but, neither, none, and who. If you read a problem and you see these words in it, they're your clues that you have some type of intersection. U is the union operator, and it's our OR operator. You don't want to use the union symbol, use the word OR. If I write probability of A union B, that is how it's read, and it is also commutative, meaning it doesn't matter the order of listing. Other words which indicate a union are and or, at least one, and either. If I want to talk about some event not happening, we do that with the complement. P of A not is read, probability that A will not occur. Other notation that indicates a complement, other books sometimes use a superscript C or a bar across the top or a tilde sign in front of the symbol. And here's the one that gives statistics students the most trouble. It is your conditional probability. And this is how we update our probabilities when we learn market information. We need this conditional probability. What's the probability of A, the product being successful when marketed nationwide, given that the B, the test marketing, was successful? So this reads, what's the probability that A will occur? What's the probability that A will occur given that B has already occurred, or that we've assumed that B has already occurred? So again, this is very important because it's how we update probabilities as we learn information at market research from our various markets. Words that indicate a conditional probability are given, when, assuming, of those, if. Any of these participle phrases that you get, if something, something, then, is automatically a conditional probability. The probability of A given B is not equal to usually the probability of B given A. It is usually not a true statement. It is not commutative. For example, if B is the event, a face card is, you cut the deck and you saw a face card, there's 3 face cards, Jack, Queen, and King in the deck. And if A is the event, we saw a king. So given that it's a face card, what's the probability of a king? 1 in 3. But if you switch those around so that A is given a king, what's the probability of a face card? Answer is 1. It has to be. It automatically is a face card. So those probabilities are not the same. They're not interchangeable. On problem 1, page 1, we have a little exercise in reading a English statement and translating it into our new probability shorthand. Ruby Rugburns signed a prenup agreement when she became the trophy wife of a wealthy widower 40 years her senior. I know this is, who wrote this trash? I did. Her husband, Al Heimers, is suing her for divorce on the grounds of infidelity with the entire Miami Heat basketball team. Ruby has hired divorce attorney specialist Tess Damoni, who has filed a petition to have the prenup agreement overturned. Gloria Allred, I guess, was busy, so Tess is stepping in. Tess has made the following probability estimates shown below. So in each of our problems during the semester, we'll start by establishing some notation for whatever events we're interested in discussing. So given in this case that A is the event, agreement will be overturned, and J is Judge Judy will hear the case. So these are the two things that we're, two uncertainties that we're concerned about in this problem. Part A says, what's the probability that the case being overturned is 0.3. So we would simply write for that one, P of A is 0.3. The probability that Judge Judy will hear the case is 0.2. Yes, it's that easy. It's just probability of J is 0.2. There's a 5% chance that Judge Judy will overturn the agreement. Well, two things are happening here. Judge Judy definitely got the case, and the agreement is overturned. And those things are happening simultaneously. So that would be the probability that Judy heard the case and overturned the agreement, 0.05. The probability of the agreement being overturned decreases to 0.25 or 25% if Judge Judy hears the case. If Judge Judy hears the case, it's going to be /J. If Judge Judy hears the case. Assuming Judge Judy hears the case, what is the probability in the future that the agreement will be overturned? 0.25 or 25%. The probability that the agreement will be overturned, but not by Judy, is 0.25. If we look at our list of words, the word but is an entry under the intersection sign. So the agreement was overturned and not heard by Judge Judy is an intersection. These two things both happened. These two events both happened. Probability is 0.25 on them. And finally, the probability that the agreement will be overturned or heard by Judge Judy is 0.45. And for that, we would write A union J equal 0.45. So those are the symbols, and there's a little practice in how to take an English statement and translate it into the appropriate symbol. Okay, now let's take a look at our probability rules. And for every topic I do this semester, I will show you an example first before we talk about the theory per se. And we'll see how we use it in practical senses before we get bogged down in the theory. Anorexia, on problem 2, is the head of product development for Slim Fast Foods. The company is currently test marketing a new diet cookie in grocery stores in the Phoenix area. Pretty good test market area. Aggressive ad campaign using local television stations to introduce the new cookie is part of this test marketing project. In order to get feedback on the test marketing, Anna commissioned a random sample of 200 individuals purchasing diet foods in the Phoenix area. And the cross-tabulation of the results produced the following contingency table. This is also called a two-way matrix or a two-way listing of data. When I have two different variables, in this case is product purchase, whether or not we purchase SlimFast or not, and gender, and I cross-tabulate the results, then we get this thing called a contingency table, and it tabulates the frequencies of each of the observations that fall into the different categories. A person who just purchased a diet cookie is selected at random, assuming that the sample is an accurate representation of cookie purchasers in general. What would we conclude? So if I take my cross tabulation After I establish my notation where S is the last people who last purchased Slim Fast and F is for female, putting in our notation, we get our observations with S and S naught and F naught in the column headings for the S's and the row headings for the F's. In order to convert these frequencies to probabilities, I take the total number of observations we have. We have 200 observations. We stopped 200 people purchasing diet products, and we asked them 2 questions. What's your gender, and what brand of diet cookie did you last purchase? So if I take the 24 and divide by 200, I get the 0.12, and the 12 gives me the 0.06, 36 divided by 200, 0.18, and so on through all of the cells in our cross tabulation. And now I have probabilities. Part A says, what's the probability that the individual last bought Slim Fast? And so we look on here, S, probability of S, 0.18. So I would write probability of S equal 0.18. What's the probability that the individual is a female who last purchased Slim Fast? I go to my table and I said female. Female's in here. Who last purchased Slim Fast? Okay, right here. So I would say the probability of S and F equals 0.12. And there we go. What's the probability that the individual is a female who last purchased another brand? Female who also fell into not purchasing Slim Fast, right here. It would be the P of S naught and F, or 0.68. Again, the listing of the order of the F's and the S's in here doesn't matter. So that gives us the F and S naught equals 0.68. What's the probability that the individual is a female or last purchased Slim Fast? Did I skip one? No, I didn't. A female or last purchased Slim Fast. So if we're in either this column or this row, we take care of females who purchased Slim Fast, one or the other or both. Have at least one of the 2 categories. So I could take this piece plus this piece plus this piece, and that would cover it. A couple other ways to do it. I could say, well, let's take the probability of Slim Fast. Let's add to it the probability of female. And that covers, the first group grabbed those, the second group grabbed these. It's okay, I covered them all, but I double counted this first cell. So I could take the 0.18 plus the 0.80 and subtract 0.12 and get my probability of one or the other or both. And the last way I could do it is all 4 of these add to 1, and I want all of them except this. So I could take 1 minus this and also get my target area, 1 minus 0.14. And these are the 3 different methods that I've illustrated here on how we could find the various parts. They all add to 0.86. If the individual is a female, okay, jumps off the page and slaps you in the face. If female, what's the probability that she last bought Slim Fast? Well, what that means is we are in this row. If the person is known to be female, okay, then we're either going to fall in this column or this column. So of this 80% of the group of the purchases that are female, what's the probability that we're in here? It would be 0.12 over 0.80. Okay, we know we're in this row. And there's the probability of being in that row, and we divide that into the probability of being in this column to get the ratios of this area to this area. And by doing that, I take the 0.12 divided by the 0.80 and I get 0.15. If the individual is a male, what is the probability that they last bought Slim Fast? So we did the market segment among, the purchase rate among females, 0.15. Now we're doing the purchase rate of this product among males. That's what it represents. If the individual is a male, given F not female, what's the probability that he last bought Slim Fast? So we would be up here in this situation. We'd be in this row are the non-females, the males. Okay, and this 0.2, how many of them are in this cell? 0.06. So 0.06 divided by 0.20 is the probability of being in there, and that is 0.30. And what's our conclusions? So if we look at the data, first off, looks like we're doing pretty good. We got our market segment is about 18%. For a new product, we've already commanded 18% of the diet cookie market in Phoenix, it appears. It appears we're doing very well. Also, who's the main buyers of our product? Women, on a 4-to-1 basis. 4 women buy cookies for every 1 male. So the advertising message, if we want to have the greatest appeal, should appeal to women as the main target, unless we're doing a real focused advertising against males. So how are we doing? Well, 18% of the people purchase Slim Fast, but if you're a female, it drops to 15%, meaning our message is not working well with women. Who's it working well with? Men. It jumps to 30% among the male population. So whatever our advertising is, it is being very effective with the male group who's buying the products, but they only make up a small portion of the buyers of this product. So we maybe want to get another ad going. This ad seems to be particularly effective with men. We probably need to get an ad going that's equally as effective with females to tap that market that we're not reaching now. The market for females is 4 times bigger than the market for males in the diet cookie business here. So that's what I would interpret from those data. These, we've looked at the first 4 of our 5 rules in our example. This early work in probability theory was done by 2 French mathematicians, one Blaise Pascal, fabulous name, Blaise Pascal, great first name, Blaise, and Pierre Fermat. So rule 1 says the probability of A plus the probability of A not equals 1. So probability of A happening plus the probability it won't happen equals 1. When the person on the Weather Channel says there's a 20% chance of rain, we know there's an 80% chance that it won't. Rule 2 we saw in our intersection table, that when we did a column or a row, When we added up the column or the row, we got the probability of the event by itself. Rule 3, we saw like 3 versions of how to calculate the union. And we illustrated in our previous example, Rule 4, which says, if you want to find the probability of A given B, then you take the probability of B by itself and you divide that into the probability of these 2 things, whatever's listed here, with an intersection sign in between, with those 2 things with an intersection sign. We take the probability of A and B and divide by the probability of B, then we get the probability of A given B. Statistical independence we will look at in the second part of our lecture today. Here's a quick visual proof of these rules 1 through 4 using the Venn diagram created by John Venn, English mathematician. He was not the originator of it, although I do believe he did it, created it on his own. It was done like 100 years before by probably the greatest mathematician who's ever lived, the Swiss mathematician Leonhard Euler. His name is pronounced Euler. So rule 1 says probability of A plus probability A naught equals 1. The sample space is everything that can happen. We are going to land somewhere in this sample space with probability 1 because it's the exhaustive list of everything that possibly can happen. Probability of us being in the sample space is 1 by definition. If we say, hey, all you A's have a group hug, and they hug each other, and they're here, what proportion does A make up of the sample space? That's the best way to look at probability is what proportion does A make up of the sample space? And A naught makes up the other proportion of the sample space. The sum of those 2, of course, is 1. And we used that when we did probability A plus probability A naught and got 1. That's how we used that. And we used probability B plus probability B naught equals 1. We used that in our intersection table. Rule 2 says probability of A and B plus probability of A and B naught equals probability of A. We used that in the table, probability of A and B plus probability of A and B naught, sum to probability of A. We added these down. Okay, we got the 4 same intersection pieces that we listed in our intersection table. They're just depicted slightly different here. But if we take probability of A and B, which is here, probability of A and B naught, which is there, we just get the probability of A by itself. Union, anywhere in the darkened region is the union. And I have 3 ways to do it. I can, here's A and B naught, here's A and B, here's A naught and B, add the 3 pieces. That's one way. I could take A or B, add those 2 together, and then subtract the common region to get a uniform coverage like we do here. That's another way. Or I could take 1 minus everything out here in no man's land, A naught and B naught. Anything that's not in the clear area, the white area, is a shaded area. So the complement of A union B, A or B, at least one of them, at least one, the complement of at least one is none. Neither of them happen. So any of the 3 that works for you is fine with me. And then finally, for the conditional probability, originally we didn't know where we were. Here's our situation. Here's A, here's B. Could be here, 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 could be anywhere in here. But as soon as you say B has occurred. Then our sample space changes. It compacts. When we learn market information, our sample space is compacting and contracting and changing shape. And rule 4 updates the probabilities for that. It is quite important. Our new sample space is everything that can happen is B. We know we're in B. B is our new sample space. Now, what the probability that A occurred? Well, it's what proportion this darkened area makes up of the new sample space. That's what probability is. It's what's your percentage area. What proportion do you make up of the whole sample space? Well, what is this area? It's the area A and B divided by our new sample space, which is B to, which is to scale everything. Then we get the appropriate probability. So this rule updates probability as we learn more information. Okay, adding a couple more words to your vocabulary. Mutually exclusive means that two events never occur at the same time. A and B are mutually exclusive if the probability of A and B equals 0. They never occur at the same time. Pictorially, they never share an overlap at all. This phrase is also called disjoint, although that's not a phrase that is in favor right now, although mutually exclusive is in favor. So you're in a meeting and you're looking at possible acquisitions, and you have two different acquisitions, and you say, well, these are not mutually exclusive, meaning maybe we could get enough financing and acquire both of them. They're not mutually exclusive. They could happen at the same time. Another good term to add to your vocabulary is collectively exhaustive. Two events are collectively exhaustive if between the two of them, their union covers the entire sample space. Not particularly useful for two events. If we have a whole series of events and we say they're collectively exhaustive, we're saying that they cover the entire sample space, that they cover everything that can possibly happen. So the probability of A union B, if it equals 1, they are collectively exhaustive. They cover the whole sample space. Also, if the probability of neither of them happening is 0, then they are collectively exhaustive. Example of that, using that, back to the same situation, we're looking at these two companies that we might want to acquire, and you say, well, these aren't collectively exhaustive. It means that maybe we might want to consider something else, that this is not the list of all of the alternatives that are available to us. If something is mutually exclusive and collectively exhaustive simultaneously, it's called a partition. And a partition is when we take a sample space and cut it into, a jigsaw puzzle pieces, where all of the pieces together form the entire picture, and the pieces have no overlaps. And a good use of that is if we say, let's go to our market and partition it into these segments so that we can control things better. Okay, an illustrative problem of these rules, and to also illustrate what happens when we do not get a complete cross-tabulation table, let's take a look at page 1, problem 3. Gene Poole is the personnel manager at Amgen. He recently reviewed 300 applicants for several financial analyst positions that Amgen has open. 60 of the applicants hold MBA degrees. Each applicant was given a financial principles competency exam. 135 passed the exam and were not MBA graduates. 15 MBA graduates failed the exam. So here we got two things going on. I don't know whether or not the person I'm looking at, of these 300, has an MBA degree. And I don't know whether the person passed the exam. So M would be an appropriate choice for a person with an MBA. P is not a good choice for pass the exam. You can use whatever you want for your labels. Just stay away from P because we got probabilities up the kazoo here. Also probably stay away from O's because they look like zeros, and I's because they look like ones. So here we go. I set up my cross tabulation table, and first I put in my 300. And then I put 60 of them held MBAs. And given my great mathematical competency, I can deduce that that's a 240 right there. 60 plus what equals 300, 240. Next, 150 of them passed the exam, so they're in this row, but we're not MBAs. MBA, not MBA, right there. This is the people who passed the exam and were not MBAs, and there were 135. All right, so let me think. That has to be 105. And lastly, 15 people were MBAs who failed the exam. This is a column for MBAs. Here's the row for failing the exam. 15. And we get the full cross tabulation table here. This time I'm not going to divide by probability by the 300 to make them probabilities. Let's just do it straight off of our contingency table. Just divide everything by 300. You can also do that. That's fine on the exam for me. What portion of the applicants passed the exam? So here's E. The portion would be 180 out of 300. So 180 out of 300 passed the exam for a rate of 60%. What portion of the applicants were MBA graduates who passed the exam? MBA graduates passed the exam. Who, if you look at your list of words, who is an intersection. It is an and. I'm not assuming that one or the others of these happened before and then the other may happen in the future. I'm just assuming that here and now, what's the probability that both of these things happened? The who is an intersection. So this would be 45 over 300. What portion of the applicants were either MBA graduates or passed the exam? So let's use the formal rule 3 for the unions. So we take the probability of M, which is 60 over 300, probability of E, 180 over 300, and then subtract the double counted area, 45 over 300 would give me the probability of the union. If the applicant is an MBA graduate, what's the probability of passing the exam? Okay, so if we are an MBA, so given we're, all right, given we're in this column here, of the 60 people in this column, 45 over 60, what's that, 75%? 45 over 60 had MBAs. I'm sorry, passed the exam. Of the 60 people in this column of MBAs, 45 or 75% of those passed the exam. Okay, so that's what I did here. 45 over 60, and got that. Or if we look at the actual formula, it says take the probability of M, which is 60 over 300, and divide by the probability of E and N, which is 45 over 300. Either way, we get the 0.75. So at this point, I'm a little bit surprised at that. I would expect it to be, considerably higher, because overall, 60% of the people passed the exam, the applicants. And that included some without degrees, some with bachelor's degrees, some with masters. I don't know if they had any PhDs, didn't say. Uh, so the MBAs only jumped up to 0.75. So what does that mean? It means there's a lot of people in here who don't have MBAs from CSUN, because the CSUN MBAs automatically pass the exam with probability 1. I can guarantee you, based upon the rigor of our MBA program. So we must have had some Pepperdine MBAs as applicants, and some Los Angeles State applications as part of this pool here, or from some liberal arts colleges around the country, maybe. If the applicant is not an MBA graduate, what's the probability of passing the exam? So if M not, what's the probability of passing the exam? Well, given we're in this column here of the 240 who don't have MBAs, 135 out of 240 passed, and 1 out of 240 didn't pass. So we take the 135 over the 240 and get 0.56. Notice that's not really that different from the overall passing rate. So again, that's the quality of the MBAs is not as high as I would have expected. Are the events independent? I don't know what that is. I haven't defined it yet. We will do that in part 2 of our lecture. But independence means they are not related to each other. Is holding an MBA, does it change your probability of passing the exam? Yes, it does, but only slightly. So they are not independent. They are dependent, but not as dependent as I thought they might be. Are they mutually exclusive? Is the probability of their intersection 0? No, it is not. They are not mutually exclusive. Are these events collectively exhaustive? Is the union of all their events, these two events, does it equal 1? No, it does not. So they're not mutually exclusive and not collectively exhaustive. Very good. Thank you.